So, first of all, thanks to Debayan, Subhadeep, and Purushottamda for inviting me for this meeting that is going on for last how many years now? It's already 10 years or more.
12 till today, so 12 years.
12 years. Okay, great achievement actually. So just to be aligned with this meeting, I'm going to talk about mechanical responses of disordered solids, and in bulk and in nanoscale. And you'll see that I have an ambitious, ambitious plan to talk about too many things. I will give a brief introduction about what I'm going to talk about, and the aspect will be basically shear banding and how to anneal basically material and the glasses and see what kind of failures that you're going to see in the system. Then, so basically these are plans. So I am going to talk about little bit briefly about how to produce very well annealed glasses using something called swap Monte Carlo methods, and then talk about shear bands. And also then next I will come and discuss about how to tune shear bands using something called microalloying and impurity particles. Then I will talk about briefly again annealing glasses using cyclic shear and what kind of effects it has on yielding processes. And then the fourth one is on along the same line, but using slightly different technique using an active particle, a run and tumble active particle. And I will show it has a fantastic, actually striking similarity with cyclic shear. And if I have time, then I will go into shear band at nanoscales, particularly in nanopillars, and I will talk about how geometry affects. And again, if I have time, then I'll briefly talk about memory formation and how a nanopillar can actually store information. So I probably don't have to talk about show you these slides, because I'm sure you have seen these slides in multiple locations. But at least just to briefly tell you that these glasses are there in our everyday life, particularly metallic glass, emulsions, colloids are there in all forms of life, particularly like in paints and then ketchup, glaciers, and makeup materials. But what is more interesting nowadays is the use of these materials at small scales, particularly at nanoscale, because of easy processing of these materials. At small scales, these materials turns out to be a very useful material for fabricating various nano devices, and they have lots of uses. And even for recently, there are this micro fuel cell where bulk metallic glass pillars are used, because these pillars will have a large amount of surface area, and the catalysis can be significantly large. But the question that remains is that for this, when you go to such a small scale, is your mechanical property remain very similar to your bulk, or is there significant changes with size reductions? Okay, so I'll briefly discuss that aspect and show how geometry plays important role, particularly at small scale. So this I don't have to really tell you that glasses are one of the strongest materials that one can define and one can obtain, but it has these major problems of catastrophic failure, which is what is known in the physics literature as yielding transitions. Even though we can make very strong materials using glasses and various combinations of these alloys, but how to stop their catastrophic failure is something which is a subject of long debate. And also there are interesting aspects, for example, recent days where you try to basically have a window to see through what is going on in a nuclear reactor. So last December, I went to a center in Kolkata called CGCRI, Center for Glass Research and Glass and Ceramic Research Institute, and where I saw how they actually build to make glasses which are called radiation sealed window for nuclear reactor. And this is very fascinating to know that glass is one of the best option to basically seal the radiation and store the nuclear waste in a safely manner. So there are significant amount of interest even in that direction. So, but there also one needs to basically understand how to basically stop such fracture processes, because they will be under in extreme conditions. Well, why is problem so hard? And this I am giving a physicist perspective. When you try to understand yielding process and deformation in crystals, they are controlled by basically defects. And if you study defect dynamics, that more or less that can be a good tool to understand basically crystal plasticity. But when you talk about amorphous solids, as the whole structure is disordered, it's very hard to define what is defect, and then identify and basically study defect dynamics. So, but recent days there are significant progresses made even in that directions, and it is sometimes believed that this SLV structures, which are basically quadrupoles, when they appear when you apply various types of deformation, be it simple shear or uniaxial or even uniform expansion. But it's not so easy to talk about these objects as basically non-interacting defects and write down dynamics on those defects. So there are attempts, and one of them is this famous work on shear transformation zone theory by Langer and the co-workers. And so there are significant progress made along that line, and which suggests that these SLVs, if they line up, then they basically produce shear bands, and that leads to basically crack formations. And it has been shown via energy considerations that SLVs lining up is an energy minimized configuration. This is the work done by one of my collaborators from IIT Bombay, Atul Dasgupta, with Itamar Prokachia, my former postdoc advisor. So this suggests that we need microscopic information to understand this plasticity in disordered solids before we actually scale up to study large materials in a coarse grain length scale. Both are needed, but microscopic informations are essential. And if we can supplement this microscopic information in a large scale modeling, particularly via finite element modeling, that will be much more closer to reality than what the current scenario is. And so what is stopping us to get a very detailed microscopic understanding of this phenomena is the lack of access to very low energy glassy states. For example, in molecular glasses, you can get glassy state which is accessible in experiment, where the viscosity can be 10 to the 12 or 13. But you do not get the microscopic details of or the arrangements of atoms and their structural information. So some of these can be bypassed if you do experiment, because there you can actually study them and do a microscopy, video microscopy, and track individual particles. But the difficulty comes when you basically try to access a very large window of relaxation time or viscosity. So here in colloidal experiment, the largest viscosity change that you can study is order of 10 to the 4 to 10 to the 5. And when you come to basically simulations, there also the biggest difficulty is the time scale. So the largest change in viscosity that one can study is now if you push it a little bit more, it can be 10 to the 5 to 6. So these are very, very similar to what you can achieve in colloidal experiments. So, but in last, I think around 7-8 years time scale, there is a significant change in what we have in basically various numerical techniques, and one of them is the swap Monte Carlo technique that I'm going to briefly talk about. So this is the technique which has been devised at least 10 years or even more, I think 14 years ago, by Giorgio Parisi and his PhD student Thomas Briguera. So what they propose is that you do simple Monte Carlo simulations, but you introduce additional step of swapping two different particles. and use the same metropolis algorithm to accept those moves. And so this may sound a very trivial kind of change in the molecular in the Monte Carlo method, but it turns out this is one of the best way to increase the relaxation process. And I will show some result soon that just by swapping two particles which are of different types, particularly if you, this will be useful only if you are dealing with systems which are binary or polydisperse. For example, in a binary liquids, you can actually take a big and a small particle and swap their positions. And one can easily see the difficulty. So in a dense environment, a smaller particle can easily be replaced on a place of a bigger particle. But the bigger particle cannot be put in the place of a small particle because it is going to overlap with the other particles. So this will be energetically very costly. So that's why the moves will be very, very rare. And if you are dealing with binary mixtures, the acceptance rate sometimes goes in 10 to the minus 5 or 6. But surprisingly, even with that small acceptance rate, the dynamics can be speed up significantly. So this one can actually make progress, and this was I want to give credits to Giorgio. When I was coming back from Rome, he suggested, why don't you try using ternary particles, where you have small, medium, and a large particle, and the swap will be then done on a basically sequential manner. A small and a medium can be exchanged easily, and a medium and a large can be exchanged subsequently. So this will enhance your acceptance rate by a significant amount, and one might be able to basically equilibrate the samples much faster. And so I came back to Hyderabad, and some years went by before I actually took it up, and I discussed this with Itamar, who was my first postdoctoral mentor, and we did this work together. So we actually introduced a ternary model, a ternary glass former, and the model particle size ratios are such, and that this acceptance, swap acceptance rate went up by at least factor of 100. Still the rates are in 10 to the minus 3 or around minus 2 to minus 3, but that itself was large enough to accelerate the dynamics very, very significantly. And we could reach or equilibrate the sample at a temperature where estimated relaxation time can be as large as 10 to the 10 to 12. So this is nearly impossible in using any conventional methods. And so this I'm saying the estimated time scale because this is the place where you do not have an idea about what should be the relaxation time. If you fit your data of your high temperature data up to these areas via various forms, the lower estimate turns out to be at least 10 to the 10, which is at least few fold speed up in the dynamics. And using that, we looked at basically various dynamical property and static property, particularly computed correlation length, static correlation length, and found for the first time that a static correlation length in this system can grow by at least factor of 5 or 6, which was impossible to achieve before, and all previous literature data showed static correlation length growing by factor of 2. So this was a significant advancement in terms of how you can access low energy glassy states, which was later picked up in this work, particularly by group of Ludovic Barthier and his collaborators. So they took polydisperse systems where you have a continuous size distribution, and then they basically tune various parameters, including what should be the distribution, the shape of the distribution itself, and were able to tune this the swap efficiency to a scale which is remarkable. And some of their papers, at least in this paper published in PNS, reported the speed up is order of 10 to the 6. And similar studies done in 2 dimensions, the speed up was achieved to be around 10 to the 10, which is enormous. And it was been claimed that one can reach glassy states, which even with experiment will be nearly impossible. So now with these advances, we are in a phase of glass, which can be compared easily directly with an experimental glass at least. And what people looked at is basically took this glasses, which are called ultra stable glasses, and seared them. So I'm basically click the three movies. So extreme left one is for poorly annealed glass, and you see that there are a lot of plastic events happening in various parts of the sample. And in the middle one panel is a moderately annealed glass, which you can achieve even with simple molecular dynamic simulations. But on the extreme right, you have an well-annealed glass prepared with a swap Monte Carlo. And you see that, the plasticity, which is color-coded using this non-affine displacement, which I'm not going into details, is very different. Particularly in a poorly annealed glass, you see that plasticity is happening everywhere, and it's kind of a homogeneous yielding process. In a moderately annealed glass, there is some signature of localization of plasticity. But in an oil annealed glass, you see a very, very clean localization of plasticity. And this is what the shear band. So now, even in computer, one can easily generate shear bands and actually study what leads to such shear band formations. So there are interesting proposals by the same group is that so this shear banding process in ultra stable glasses are kind of a first order non-equilibrium phase transitions, which has been debated a lot in the literature, and is not clear what it is. And it's also been claimed that when you anneal or change your annealing history, you are basically going through in a phase diagram where you have a first order phase transition terminating at a second order critical point, and the physics seems to be claimed to be belonging to the same universality class of Ising model in a random field. As I said, these are theoretical development that has been debated strongly, and there are no clear-cut answer yet. But it's very, very clear that as one looks at these shear bands and increased system sizes, the stress drop, as shown in basically the panel A, it becomes larger and larger. And if you look at the corresponding susceptibility, which talks about how much fluctuations you have around this yielding process, where the shear band appears, that susceptibility turns out to grow with increasing system size. And this somehow signals that there is a large length scale which is coming up, and this length scale is obviously connected to the spanning shear band that one sees. So then we basically asked this question where Pinaki joined. So actually, so this is the work we did 4 years ago with Pinaki, where we try to look at how to control such shear bands, and can we get a better understanding of what leads to homogeneous to heterogeneous yielding. So this is the work that was published in PRL in 2019. So the concept that we used is this microalloying. So our crude model of microalloying was to actually fix a few particles, and that we call pin particle, and we do it randomly, and this is the reason why this is called random pinning protocol. And using this method, what you just basically choose a set of particles randomly and you freeze their position. But when you deform them, then they can move affinely, but all non-affine motions are suppressed. And we looked at basically yielding process in this kind of scenario. And what we found, which is displayed, I hope you can see my mouse in this panel where we plot stress versus strain. And you see that when you increase the degree of pinning or the pinning concentrations, then basically material becomes much stronger. The modulus here, modulus goes up significantly. The stress peak goes up, but the peak becomes broad as well. And also notice that the yield point shifts to larger strain. So the system actually was able to support much more load than basically a non-pinned usual glasses. And when we looked at basically the spatial map of plasticity, we see that when you do not have any pin particle, then you get this low panel data set or the maps where you get basically clear shear band type behavior. But when you have some amount of pinning in the system, then you get an homogeneous yielding. So this is signified by this stress peak, which is broad. So this random pinning is not a very ad hoc thing, because it's also been experimentally realized in the group of Rajesh Ganapati and Ajay Sood. So they were able to do laser trapping and looked at various dynamical and mechanical properties of this pin system. So there is a very large literature which actually started from this direction. So then the next question that we had in mind, how to do microalloying, which will be applicable even in, let's say, in experiment, because this kind of random pinning will be impossible to achieve. This is doable in colloidal experiment, but not in molecular experiments. So we propose that if we actually introduce particles which are bigger in size, then this big particle will have basically relaxation which are times which are much larger than your host. So they will have much smaller diffusion coefficient than the medium particle. And over a time scale of the medium relaxation time, this particle can behave as like a soft pin particle. So we tried this concept and studied the yielding process in a setup where you introduce particles which are twice the size of your host particle. So this is signified or demonstrated in this figure in the right top left corner. So we took basically particles which are of diameter twice, and we looked and you just basically change their concentration. We do see that the yield point moves to larger strength, and so it has some pinning like effect, but it's not fully what you can get it in a random pinning. But it produces some effects which we feel is a signature of a pinning like effect. And then we went on with the idea, instead of basically using a large particle, we thought of introducing an elongated particle and to see whether they can be better pinning sites, because a long particle will have various dynamical restriction in terms of both translation and rotation. Particularly in rotation, they won't be able to rotate as freely as a spherical particle. So this is what we looked at in this scenario. We basically took a system and introduced dimers. And the dimers, when you increase their concentrations, then what we see is that when you have the zero basically dimer concentration, then you get usual stress strain curve, which is represented by this brown symbols in panel B. And then you gradually introduce your dimer concentration at for large enough dimer concentration, which is around 10%. Then you see that your material becomes much more strong in terms of enhanced shear modulus, and also the peak position moved significantly. So your yielding has been delayed by a very significant amount. So these systems are able to support loads by large amount. Sorry. And if we compute the susceptibility, so it turns out the susceptibility peak increases very rapidly with increasing number of dimer concentration. So that is signaling some sort of shear band formation. And indeed, when we look at the spatial map in terms of this non-affine displacement, we see that already in the samples, you start to have some shear band. But major achievement in this dimer simulations was that the yield point would be shifted by significant amount. So then, to just for sake of theoretical curiosity, so what student did, he stopped the rotational degrees of freedom of these dimers. So the dimers in the simulation can no longer rotate. So they are frozen by hand. So if you do it and then look at the same stress strain curve, then we see that the stress strain curve becomes very different. Now it becomes, the yielding becomes extremely sharp. which is signaled by the susceptibility. The susceptibility peak went by at least 10 to the 4, factor of 10 to the 4, which is huge, which tells us that the rotational degrees of freedom of these dimers are extremely important for promoting or stopping this CR band formation. So what it does when they cannot rotate, so they somehow concentrate all the strain or localize all the strain to form CR bands. So which you can see in this snapshot. So when you have some amount of dimers, then you have some CR band, but CR band is somewhat diffuse in the sense that it is not, so the width is significantly large. But if you increase the dimer concentrations to at least 5% or 10%, then the width, the CR band becomes extremely narrow. And that is also signaled by a very sharp stress drop in panel C, which is, yeah, so this was supposed to be A, but I have taken it from the paper itself, and it's a cut and paste problem. Sorry for this. So this gave us this crucial hint that if you try to microalloy materials to improve their material property, particularly the modulus, and then this elongated particles can be good choice because the modulus increased by a very significant amount. But it also promotes CR bands if because of their rotational hindrance. So in these simulations, the rotation was frozen by hand, but in reality, if you need CR band to be present in your system, that you can achieve by introducing long rods. So if you increase your impurity rod length systematically, then what we found is that you can indeed achieve the same scenario what we achieved when you basically freeze the rotational degrees of the rod particles. A long rod obviously stops, long rod will have very large hindrance for rotation, and they lead to very clean CR band formations.
There's a question, Shorjit.
Yes, yes.
Yeah, so the susceptibility is just an overlap function, right?
Susceptibility is, yeah, so you basically compute the standard deviation of that overlap function, yes.
And if you have like a plus kind of particles, I mean, will it hinder the rotation instead of just
the plus, yeah, if you have that kind of particle, yeah, we haven't looked at, but they may be a good choice because but they also have rotational difficulties as well. But whether they will localize CR band or they will diffuse it is something which I don't know. It looks like promoting CR bands in a particular region. But also note that in this snapshots, rods are actually distributed everywhere. It's not that they're all aligned in the CR band. But somehow their presence leads to much sharper CR band formation.
Are these like shear bands devoid of those the elongated rods?
No, they are uniformly everywhere. It's not that their concentration increase in the shear band. It's not the scenario. They are still uniformly distributed in the sample, but somehow shear band are much thinner.
Do you allow them to, when you share the sample, like do you allow them to move or not move? I mean, I understand.
In this scenario, they are free to do both rotation and translation. But just because they are elongated, their rotations are hindered very, very significantly.
Aspect ratio.
So here the aspect ratio is around 2.5. It's not very long, but I think 2.5 particle diameter.
Thanks.
Yeah. So then we wanted to actually do some structural analysis, and this is so we took up this work of Hajime Tanaka, who looked at basically how the particles are packed in various local regions, and this is the Tanaka order parameter, which basically looks at in 2D the angles of your nearby particles and the distance, and then you can compute that order parameter. In 3D, you basically look at the tetrahedrons around the particle. And when we basically introduce rods, and if you increase the rod length, then it turns out the Tanaka order parameter decreases significantly. So smaller value of the order parameter means that you are much more stable. So larger value of the Tanaka order parameter will lead to more disorder in the sample, or basically loose areas. So this rod somehow helped us to achieve something which is very pinning-like. Pinning also makes your sample become much more ultra-stable in that sense, or by increasing CR modulus. And the rod seems to be doing something very similar. So we also compared the amount of, or the degree of structural ordering in this, or I should not call structural ordering, structural stability compared to ultra-stable glasses. And it seems that this elongated rod and their concentrations can give you a glass whose stability is somewhat comparable to this ultra-stable glasses using swap Monte Carlo. So this is an interesting way to achieve stable glasses, although we could not stop CR bands. So sometimes basically the CR bands are promoted, but the yielding process is delayed. So this has this good one good advantage is that the modulus goes up if you increase the amount of long rods, and your yield will happen at a large scale. But when it happens, it will happen in a catastrophic manner. So the CR band something which we could not stop or diffuse. So this is though it has some pinning-like effect, but it's not similar to what pinning does. So if you then look at basically the CR band and then cut through the profile itself, and you see that the order parameter is very large in the CR band region. And interestingly, outside the CR band, the order parameter is much smaller than your undeformed sample. So whatever the average structural order parameter of the sample, and if you compare the same structural order parameter in the non-banded region, they turned out to be smaller than your undeformed sample, which telling us that somehow the non-banded regions became structurally much more stable, which is a surprise for us, and we don't have an answer to it. And hopefully in future we'll be able to get a good understanding by doing a better structural analysis of this, both the banded and the non-banded regions, because producing the CR bands are now is much easier for us in computer. And and we also looked at basically if you cool your sample at a different rate, which is basically defined by this parent temperature T. If you basically go to very low temperature and then you cool, versus if you take a high temperature liquid and cool, so that will give you a different cooling rate in some sense. And you do it if you prepare your glass from a high temperature liquid, then you get a CR band which is much more diffuse. But if you get it in a well quenched glass, that will have a CR band which is significantly narrow. And so with this kind of basically framework, we are planning to study how the CR band width increases as you basically deform further after the CR band forms. And what are the other parameters which controls this CR band width? And what is the scale that appears here? So is there a natural scale that that controls the thickness of the CR band? Some of these questions are not clear to us, and hopefully we'll have an answer in the near future. So this part maybe you can, so this is a detailed structural analysis or structure around the rod itself, and I'm going to skip this part. So if we do not have any questions from the previous section, then I want to move into an interesting story of annealing using an oscillatory shear protocol. Okay, so I'm just assuming that there is no question because I have only a few minutes left. So in oscillatory shear protocol, what you do, you basically take a sample and shear back and forth in both positive and negative directions. And this has been shown that this leads to annealing of your material. It helps rejuvenating the sample. And so if you look at this figure, I hope you can see my cursor. and or I can use laser pointer. So this figure. So here it was schematically shown the average energy as a function of this oscillatory shear cycle. And if you start with a poorly annealed glass, then you can actually anneal the sample very well up to a point, and after that it heals. So and then there is an interesting energy scale. If you start your oscillatory shear below that energy scale, then it turns out that you no longer can anneal the sample using this oscillatory shear protocol. So this energy scale turns out to have a very close correspondence with what an MCT energy scale is going to be. And why it is so that we do not have an answer, nor the others who have worked on this as an answer too. But what we looked at in addition is that instead of doing an oscillatory shear along one direction, let's say in XY plane, we introduced oscillatory shear along other possible directions. Particularly in a 3D, you can have XY shear and you can have YZ and a ZX. Okay. And what we found that if you do an XY oscillatory cycle, then the energy reaches a steady state. Then you switch your direction and do YZ, then the energy decays once more and reach a plateau. And from there, if you do XZ oscillatory shear, then you can further annihilate. And you can actually have various combination of this. You can do X, Y, Z, and then repeat the same pattern, or you can have XX, XY, XY twice, and then YZ and XZ, and then repeat that pattern. So depending on what kind of pattern you want to choose, the steady state or the absorption state that you get turns out to be very interesting. For example, you see this panel where if you do unidirectional oscillatory shear on XY plane, then you get a steady state which has only one energy scale. But at the same time, if you do oscillatory shear in 3 directions, then you can reach a steady state which toggles through 3 energy states, which is very interesting in the sense that which I may come back if I have time. That these states, absorbing state, store memories. So if you do multiple direction oscillatory shear, there are possibilities that you may be able to store multiple memories along those directions, which is not yet achieved, but the possibility still holds. But what is most important and interesting is that the better annealing procedures, although the phase diagram remain very, very similar. So there also you have an energy scale below which you can no longer anneal your sample using oscillatory shear protocol. So mechanical annealing seems to have a lower bound. So this lower bound is a fundamental question which, as I said, that nobody has an answer to, and which remained as an open question. And so one interesting thing that we found is that if you do a random sequence of oscillatory shear, then your energy profile goes down, 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 and it takes enormously large number of cycle to reach a steady state. Okay, but so this tries to explore various complex paths or the minimas, and then eventually will saturate at some point because the phase diagram doesn't evolve beyond this. So this oscillatory cycle has an interesting basically side effect, and in some sense the question that we asked is that so we know that there are various types of glass forming liquids. So some glasses are strong liquids, some are fragile liquids. So we asked this question, are the same in terms of yielding process? Okay, so in this figure we have taken a system where basically the kinetic fragility can be tuned systematically by changing only density, nothing else. So this is a mixture of a 50-50 binary mixture of harmonic spheres at densities, let's say for example 0.681, you get basically a state which is more strong light, and then this state you can take and cool it to go to zero temperature glass and look at their dynamical property. But if you take a density which is 0.943, which is this black stars, then you get a very fragile liquid, and you can actually quench this liquid to get a glass former generated from these fragile glasses. So we repeated this same oscillatory shear in these samples, and for the strong case, what we found is this the phase diagram or the annealing property changes significantly. So one interesting point which we have is that if you start from poorly annealed, then your annealing goes on and on and on. At some point, it stops, and beyond this yielding, beyond this oscillatory amplitude, then you start to basically yield, and there is no longer any annealing. But the point at which you yield remain very similar, even if you increase your annealing. If you go to lower and lower energy state or better annealed glasses, your yield point do not shift. At the same time, if you look at glasses formed using this from these fragile liquids, which is this density 0.943, and look at the same phase diagram as a function of the oscillatory shear amplitude, what we see is that the yield point moves significantly with increasing annealing. So as you go to lower and lower energy state, your yield happens typically with a shear band formation, but at a strain which is much larger than what you get it in the poorly annealed glass. So this physics, it was something, at least for us, it was somewhat surprising. And because strong and fragile concepts are typically useful when you're dealing with liquids, not when you're dealing with an amorphous solids. There you are talking about brittle or a ductile behavior, and which we feel is related to your annealing protocol. But the changes in the oscillatory phase diagram for a strong and a fragile glass forming liquid, when you basically generate glasses from them, and this difference was surprising. And then we asked this question: is there a way to understand it? And and what we feel is the scenario lies in the shear band. So if you plot stress versus the strain, then what you see that in a strong glass, even if you have reasonably well annealed glasses, you still do not get very clear-cut shear band like drops. But for a fragile glass, you get a very clean shear band formation. And so we are pushing ourselves a bit more along this line, and we have to basically simulate much larger system size to get a clean shear band and to study whether indeed the strong glass former versus fragile glass former, there is a difference in the shear band, and we don't have an answer to it yet. But these observations can be actually explained if you basically do some sort of a mean field calculation of this. So this mean field modeling was first proposed by many people, and then subsequently Srikant proposed a new single site model, which is a single site model for an amorphous solid and yielding behavior. So the idea is that you can actually think of the amorphous whole solid being moving in various energy landscape. For example, you at zero strain, you are in this energy landscape. This is given by this black card. And as you strain the sample, then the system goes up in this energy landscape and then topples to new energy minima. So maybe this one, but if you do a reverse shear, then you can actually access this red minima. And so if you basically put a few such rules, then more or less you can actually reproduce all this oscillatory shear phase diagram of an amorphous solid. But what was missing in this thing was the difference that one might get if you take a fragile versus a strong glass forming liquid. And what we feel is the answer in the fact of how energy barrier changes in these two types of liquids. And then when you basically generate glasses from them. For example, strong liquids has been shown by explicit calculations. The typical energy barrier cooling history does not change. Okay, even if it is it changes at when you are in the poorly annealed regime, but you go to well annealed glass regime, then it's more or less saturated here. So this is represented by this blue curve. And if you have basically very fragile glasses, then energy barrier grows strongly with your basically annealing protocol or your temperature. And if you use this information in this mean field single site model and repeat the calculation to produce the steady state phase of oscillatory shear, we find that when you basically take a liquid whose barrier doesn't grow beyond a certain value, as you do better and better annealing, you get a phase diagram where the yield point do not move anymore. But if you take a glass which is modeled by this black curve where the energy barrier grows with annealing history, then you get a phase diagram where you can clearly see that yield point systematically moves to higher and higher strain. This suggests that while modeling this kind of materials at a coarse grain length scale, one must include these informations of barriers and how they evolve with basically your annealing protocol. And so although this is a single site model, so the talking about shear band in this is nearly impossible. So we have a joint work with Pinaki, Viswas, and Siladitya, which we are trying to develop and do a multi-site model. And we believe that that model will be able to reproduce the differences in shear bands if we see something here.
Already time is almost up.
Time is almost up. Okay. So then I will actually I will take 2 minutes and talk about the size effect, and then I can stop and take questions. So now I will give you a brief, basically show you some results which we have when you basically go to nano-scales. And this is in the literature there for quite some time, which says that if you take nano pillars and deform it, then if the pillar diameters are smaller than around 100 or nanometer or so, then you get deformation which is more homogeneous, like this bulging type phenomena. But if your samples are thicker, then you can get a very clean shear bands. And this is something similar has been shown in this paper as well. As you go to very, very small nano basically pillars and pull them and metallic glasses, then you can get basically shear bands, very, very thin neck formation. So we looked at something similar in our simulations. So these are the basically pillars which are annealed using active particles, or you can also anneal them by oscillatory shear. And I did not talk about it in details. But if you take this system, so aspect ratio is 1. So basically, you have a cubic pillar, and then you pull it, and then you see the shear bands are not very clean. But if you take a pillar which is size of aspect ratio is 2, height versus the base, then you get a shear band which is somewhat is much cleaner than the cubic one. But if you take an aspect ratio which is close to 4, then you get a very clean shear band. And if you look at the corresponding stress strain curve, then you see a very sharp drop. It suggests that it's along with annealing protocol, as you go to an open geometry scenario, your sample geometry is going to start to matter to give you the stability. So just to stress on the geometry, we looked at not the sample size. So we looked at bigger system size, 64,000 particles, but in a cubic shape, and you see that there is no shear band. But if you take a smaller system size of 32,000 particle simulation, but with an aspect ratio which is 4, then you get a very clean shear band. So this tells us that sample but smaller aspect ratio, you are going to get less shear band formation. But a smaller sample but an elongated geometry will have much more shear band. So that's why the pillars, when you basically use for any practical purposes, one has to be careful about their stability because they can fail catastrophically as well. So maybe I stop here, or because I had a couple of slides to talk about memory formation, but maybe I will skip that part because it requires some discussion as well. So I will stop here and then highlight the funding. Otherwise, they are going to raise the objection. So the research that I carried out was funded primarily from my institute at TIFR, and the money came from Department of Atomic Energy under this project. And I have a couple of basically government money from Science and Engineering Board by the SCORE research grant. And I got fellowships and Sandhya Jayanti fellowship money. This has been used for doing this research. And thanks for your attention, and we can have some questions.
Let's thank the speaker. Thank you, Saurabh, for coming to and presenting the talk. So, few questions we can have.
Yeah, Sharjit, I had a question. I have a question.
Yes.
For this, you are annealing in different directions, right? I mean, you are annealing by oscillatory shear and by sharing it in different directions. Oscillatory shear.
Yes.
What is the typical, strain amplitude that you use to anneal them?
So this system that we studied has a yield strain at around 0.07. And we basically vary the yield, the strain amplitude from 0.01, 02, 03 up to 0.06. And if you go beyond, then you do not get any annealing. You get basically yield.
I'm not talking about annealing. I'm still talking about those energy, things that you showed, and the strain.
So I'll go back and just show me which one.
Oscillatory one in different directions. X, Y, and then you're doing it in different.
Okay, just yeah. I'll just go back. Here.
Yeah. So what are the strain amplitudes for these energy plots that you are making? There is
So these are all done with I think 0.01 or 0.02 probably.
0.02. And what is the yield
Yeah.
point for?
This is again at yield point is at 0.07 in 2D, and the same model is being studied in 3D. So there it was 0.09.
0.7.
So what is interesting is this nice plateau appearing. If you basically shear it along one direction, then it saturates there. Then again, if you do it in other direction, then you again have a cascade of events and leading to a new minima. And this minima, this structure continues. So there is some sort of a compactification, which plotted in this figure, where if you can see that average energy as a function of number of basically changes in this direction. That's like a compactification process. That decays as 1/n, which is somewhat reminiscent for to granular matter. If you look at basically they have this compactification in granular matter. So there you can compute basically changes in volume or increase in density, which seems to show similar 1/n behavior. And yeah, so we have no answer, no microscopic understanding of it, but this seems to have similar behavior.
Thanks.
So there is a question from Professor Jorge Ortin.
Thank you.
Yes, yeah.
Just a curiosity, I'm not acquainted with this field, but the two transparencies that you could not show us about encoding memory, I just wanted to know whether memory is encoded in the atomic positions at the end of the cycles, or is some other encoding that you are working
on? Okay, let me let's go there. This one. Okay. So this atomic. So we computed using this mean square displacement, and this is not in the. So it's not exactly. So you are asking this question: if I come back, am I exactly coming back to the same configuration, to an atomic precision?
Yes, this is what I would like to know.
Yeah, I think I don't think we are coming back to that kind of a precision. We haven't explored it, but do you have any insight of why you think that it's not going to come back? The energy is very, very similar, at least to the machine precision that we have.
No, I have no idea. I'm just asking.
Okay. No, I think, yeah, so there are various works done which suggest that there are connected minima where the system moves around. And the interesting thing, if you give me 1 minute, which is in the next slide. So here the interesting point was that if you do multi-directional oscillator is here, then you can read in any protocol you choose, the memory is not going to be erased. But if you do it in one direction and mistakenly read in the opposite direction, then you can actually erase the memory.
Okay, that's very interesting. Yes.
Yeah, so this is what we showed. So if you, let's say, if you do XY is here to code the memory, and then you do an orthogonal XZ mistakenly, then you actually have erased the memory and you could not recover it. But if I do XY, YZ, ZX, and then reach and store the memory, then I can do any one of the methods, and I will have the same information without basically losing it.
But is
So
the
yes.
information encoded in the position of the particles at the end of each cycle?
Probably not. This is like somewhat coarse-grained and computed using mean square, average mean square displacement. So it's probably not of that scale.
So you're saying
So yeah,
values, but not in the positions of
the atoms.
yeah. I think it definitely goes to some sort of minima which are somewhat nearby and similar energy scale, and then not too far from each other, but probably not exactly the same minima in a mathematical sense, in a precision which is machine precision, for example. Let's say. It's not the case.
If I ask you a question like along the same line, so let's say like I do the same experiment with colloids. Can you point to me a good quantity to say that the system comes back to the same memory, because all that I have is positions of the particles.
So I think you can actually do compute this mean square displacement from your initial sample. So with respect to that, if you compute it, then you will see that you can actually get the signature of the memory in the mean square displacement. So for example, if you have Sayantan probably showed that this is also encoded in modulus. If you can compute local moduluses, then also modulus shows a change at that strain amplitude. So those are much more global quantities, and they do have that information.
Thank you.
Any further question? If not, then let's thank Professor Karmakar once again, Sharajit. Thank you very much.
Thank you. Thank you. And thanks for the attention and this nice, interesting questions.